Appreciate it. Thank you. By way of introduction, Joseph Idziorek. I lead product management for our non-relational database services at Amazon. One of those is DynamoDB. I've been working on DynamoDB off and on for the last 9 years, and it's been a really fun service. DynamoDB just turned 13 years old this year, so now it's a teenager. So in database years though, that's pretty good. But yeah, it just turned 13 years old, which is kind of wild. We really want to do, between myself and Lee and Aman, is just give you a mental model for some of the choices we made with DynamoDB early on and we continue to make. And really what I want to be able to do is provide context for hey, this is why DynamoDB is built the way it is. These are the problems that we are building DynamoDB to solve in the past and still remains in the future, and what you can expect out of it, and also what you can expect. It's not supposed to be the all-singing, all-dancing database. We built it for a very specific purpose. So we're going to walk through that and talk about some of those things. So we look at a lot of customers that are using DynamoDB today. So what do they all have in common, at least some of these customers, right? They have applications, very high throughput, that do the same thing over and 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 over again. Things like, give me the session state. Things like, put an item in a book, in a shopping cart. Get a player profile. Update a bank account record. Right? These are not complicated queries. These are things that are static over and over and over again. And they all use DynamoDB for that because they want that predictability. And this is why we built DynamoDB. We built it for any scale. And it's funny, when DynamoDB launched in 2012, the word serverless didn't even exist. That didn't even come into our lexicon until a little bit later in 2012. But there's a lot of capabilities that we built into DynamoDB that have persisted, and I think we continue to build upon them. So we're going to talk about 3 things today. It's how we built for any scale. We're going to talk about high availability through the lens of zero downtime maintenance, which is always a fun topic, and then we'll talk about fast, predictable performance. But really, the mental model I want you to think about with DynamoDB is an optimization. When we set out to build DynamoDB, we didn't actually set out to build a better relational database. That was never the purpose. We built out to build a fundamentally different database that optimized for a certain set of access patterns, the ones that you do over and over and over again, so we could optimize the performance and scale for those access patterns that aren't dynamic and aren't changing over time. So in kind of true Amazonian fashion, if that's what we were building, who is the customer we were working backwards from? Turns out it was us in Amazon, 2004. Amazon was Amazon.com was operating on then what was probably the most technically advanced database in the world, and we had a lot of issues scaling that database. And you can imagine how much money and technical effort we put into scaling that database. And this is 2004. Imagine the growth Amazon.com has seen over the last 21 years. We never would have made it on that database. We were hitting outages. Of all times, for an online retailer, December is the worst month. That is your highest grossing month, and it was the worst time. So what we do at Amazon is, we took a bunch, so we had the outages, and what we do at Amazon is we go through a process called a correction of error document, where we write, basically it's a deep dive into what went wrong, called a COE. And what we did as part of this COE is what we discovered in our access patterns of this relational database is that 70% of the queries are just accessing one item in a table. 20% of the queries are accessing a single table but just doing a range scan. 90% of the queries weren't using any of the functionality in a relational database, but we were paying the cost of all the complexity and all the overhead of using a relational database for those workloads. So a bunch of smart people, Werner Vogel and Swami, who now leads up our generative AI and agentic AI space, went off and built a system called Dynamo. Dynamo, very different than DynamoDB, has very similar origins, but they built a system called Dynamo, which we operated at Amazon for a number of years, and then they wrote the Dynamo paper in 2007 as a result of their experience with that system. Dynamo was really great. It was scalable. The one thing it wasn't was fully managed. So developers still internally in Amazon still had to manage and configure and do all the fun stuff of scaling a database themselves. But it laid the groundwork for what eventually became in 2012, which became DynamoDB, which was a fully managed serverless service. And now we get all the way to 2025 and the teenage years of DynamoDB. There's been a lot of innovation. There's been a lot of stuff that we continue to work backwards from customers. I think the things that we really hold ourselves to very strongly in the DynamoDB team is the original tenets for why we built DynamoDB: consistent performance at scale. And everything we do, every feature we think about, we think about through that lens of we're holding to that principle. And like, you might be thinking to yourself, Joe, consistent performance at any scale sounds like marketing gimmick to me. Like, what does that really mean? Well, so last week I was in an EBC, which is a common customer meeting type that we have at Amazon, and there was a customer that came up to me and said, Joe, we're going to grow. Can DynamoDB grow with us? We're really worried about the profile of the latency for our workload as our company grows. And I'm like, ooh, this is always a fun way to start a conversation. I'm like, what's the throughput right now? They're like, we're doing 8,000 requests per second. I was like, okay, where do you want to go? We think we're going to 10x that. Okay, no problem. We can do that, and then we can 10x it again. We can 10x it again, we can 10x it again, and after we 10x it, then maybe we can start having a conversation about like how we think about scale. And that's really what we've built with DynamoDB, and having that same, I would say, that same latency profile, because like if you think back from Amazon.com, the 10 millionth customer that uses Amazon.com and puts an item on their shopping cart, that performance can't get worse with the next customer and the next customer and the next customer. We can't have the performance degrade the more customers we have and the more successful that business is. And the same thing is true for our customers. So in totality now, we have over 1 million external customers using DynamoDB, which is just an incredible number. We really see customers using DynamoDB for really kind of two separate kind of classes of workloads. This is the biggest workload I have. This is the only place it can run is on DynamoDB. And then we have a bunch of workloads that are really small configuration, or you're doing something in the background. You just really like the simplicity of serverless, scale to zero, and not have to think about it. We really see the affinity with Lambda and the serverless stack as that progressed over the years, created a really nice coupling between Dynamo and some of our friends in Lambda. DynamoDB today, and this is just external workloads, and for folks that don't know, internally we use DynamoDB at Amazon all over the place, and it's one where we have bet our company on it, so then we trust it to speak with confidence for you also to take a dependency on a technology that we use as critically as you do as well. We have hundreds of tables over 200 terabytes. We have hundreds of tables that do over 1 billion requests per hour. We have hundreds of tables that do over 500,000 requests per hour. And this is why we built it, is to do the most demanding workloads that we have and other folks have in the industry. All right, so let's talk about distributed systems. The mental model for I want you to think about DynamoDB is think about it as a distributed hash table, right? And this is one of the ways, if you want to achieve any scale, at some point everything has to get off of one server. You can't have everything sit on one server. You're going to have to distribute the workload somehow, some way. Otherwise, you're going to be asymptotically limited by what the largest instance size is, or you have to do the manual sharding thing. So if you think about it as a distributed hash table, as a mental model, and this is why, especially in non-relational, data modeling is at a premium for non-relational, because what you're really trying to do when you access DynamoDB or distributed systems like this is really think about, I want to get the consistent performance at scale. You want to make the database do less work, right? So that's why we don't have joins, right? Because then you don't have all that server-side processing. But you also want to reduce the amount of round trips you have to the database, right? And a lot of like high-throughput applications, most of the latency is consumed in DynamoDB, not in DynamoDB, but in the network path, right? So we want to do, if you're going to make a call to a database, it's best just to make one. So which gets you into a data modeling where you think about denormalization. You're trying to encapsulate your data in a way in which you're just fetching the information you need once, you're pulling it back, you're using it, and you're off to the races. But that's why it puts a premium of data modeling onto DynamoDB, which is a little bit different than the flexibility you get in a relational model. But this is, those are the trade-offs of the flexibility of querying in a relational model, but also the consistent performance and scale you get from DynamoDB. And DSQL is going to help us bridge that gap tremendously as well. So we're really excited about that. So when you think about partitioning, and this is kind of a concept in DynamoDB as partitioning your key space. I'm going to use this little blue box for illustrative purposes. But you can think of a partition as a unit of compute, so read and write capacity and a little bit of storage in there as well. And this is how we scale things in DynamoDB. So when you create a table, you create your partition. you take your partition key, and we use that partition key for, we put it through an internal hash algorithm, and then we go place it on one of our storage nodes, and it lives somewhere in AWS. As your workload grows, what we actually do, and this is just, I mean, key spaces are infinitely large, but we'll just use a key space of just between 0 and 9. Humor me, and you can be bigger than that, but humor me on this one. As your workload goes, what we actually do is we split these partitions. We do this automatically behind the scenes. So if you're driving workload and we needed to add more, we would split that partition and put it on 2 different servers. Yes, there are servers in DynamoDB. Everything has servers. Serverless is just an abstraction. And if you continue to drive that workload, we will split it again. And let's just say, item 3 was a very hot item, most popular item on your website. We would split that down. And we actually built DynamoDB to infinitesimally split down to the smallest denomination of what you can access, which is the partition key. So, and I think this is kind of really interesting, the parallels with DSQL as well, is it's very hard to build this type of scale on top of a database that already exists. You almost have to go back to first principles and reimagine all the different characteristics of a database and build scale from the very, very beginning down to, I would say, the most primitive levels of the database. And that's kind of what we've done with DSQL as well as DynamoDB, is not just take a traditional thing and try to put something on top of it, but reimagine how we actually build databases. So we'll actually shard, if you will, or partition data all the way down to the individual. One partition will sit on or one item will sit on a partition all by itself. All right, so if you have a distributed hash table, well, the access patterns that are lend themselves particularly well to this are primary key lookups, right? Like we go back to our computer science classes, what do you want? You want a hash table lookup. That's best, that's going to be the best performance and the simplest for us to use. We also have range scans, right? We can do a range scan on a particular, on a sort key, and we can bring back, say, items, the last 10 items that were stored on a given date. And then if you can do range scans, and you can do table scans. I think the thing that's really cool about DynamoDB is these are all 3 separate APIs. So you can't do, like, say, hey, I'm going to go get an item and actually accidentally do a table scan on your whole table. That's a separate API. You have to explicitly call that. And one of the big differences between DynamoDB and relational databases, DynamoDB has an imperative API, which means you have to tell me exactly what you do, and we will do that and only that. Versus SQL, which is declarative, right? You declare what you want the database to do. Select star from foo where x is greater than y. And then the database goes and figures out how to do it, right? So it's an interesting mental model between the two of them. So where have we seen these access patterns before? Well, turns out those are the problems that we had internally on Amazon.com, and this is how we got to this architecture with DynamoDB and how we thought about this is how we were going to scale the database. This is a very simplified version of the DynamoDB architecture, but because we're talking about partitions, I'm going to focus on the green guys, which are the storage nodes. So if you think about a storage node, it's fair to assume you'd say, hey, again, ours are the blue guys. You'd say, hey, there's a storage node sitting somewhere in DynamoDB. All the partitions on that are from my table. Well, you actually don't want that, right? And the reason being is, like, imagine that thing goes away. Well, that's a lot of partitions that have to heal and have to recover. So what we actually do is we build DynamoDB as a multi-tenant system, not a single-tenant system. If you had all the data on one disk or one storage node, single-tenant system. We built DynamoDB as a multi-tenant system. And the reason being is for recovery. If you have a 10 gigabyte partition and a node goes down, mean time to recovery is how quickly can you restore 10 gigabytes of one partition on one storage node. Much simpler than recovering hundreds of gigabytes or a terabyte worth of data on a single volume. And then we take those partitions and we spread them from multiple different tables across the different storage nodes. So then your data, there's not one, let's say, a natural single point of failure, but it's distributed across a fleet of tens of thousands, if not hundreds of thousands of storage nodes in a way that helps us offer very high availability on this. One of the things that we worked on this year, which was a really big launch for us, is if you take the accumulation of all the partitions you had, so I said it's a unit of throughput, right? It's 1,000 writes, 3,000 reads, and so much storage. And you sum all of those up on the back end on what your DynamoDB table has, that's what we call what your table is capable of doing, right? So that's what your table would be able to instantaneously be able to support should your application need it. We call that concept warm throughput. So if you want to look at it in a 2-dimensional axis, as you scale your database workload, DynamoDB will automatically split partitions and be able to provide more throughput for you. But we keep that throughput around for you. We don't actually take it back. We don't claim it. We leave it there should you spike up to that workload again. You don't pay for the purple line, right? That's the warm throughput. That's what we have to manage. You pay for the blue line, just the request that you use. But DynamoDB will keep that throughput there, that warm throughput there for you, just in case you need to spike up to that point in the future. And that's a really, I know I'm very passionate about databases. This might sound like, but it's a very, very cool thing that we're able to do. And what it really help our customers do is preserve for high availability in the application. The second thing we did is we also introduced a new API this year that allows you to scale the warm throughput for your application. So if you have an event where you think, I don't know, you're going to, let's just imagine, since I'm wearing Nikes, we'll just imagine you're a shoe company, you're going to come out with the next whatever most brilliant shoe is for your company, and you know you're going to get 10x the throughput for your workload. You can call this API, scale the throughput up 10x to what your baseline warm throughput is, and then your database in DynamoDB will be ready to go for that event. And this has been really a really fun project to work on and really has been impactful for many of our customers. So with that, I'm going to hand it over to Aman and talk a little bit about zero downtime maintenance.
Hi, folks. My name is Aman, and I am a DynamoDB Specialist Solutions Architect. I've been with Amazon about 7.5 years, working mostly in the NoSQL and analytics space. So, apart from working with customers, helping them build highly scalable solutions, I'm also a fanboy of DynamoDB because I've spent so much time working on it. We also get to learn from how DynamoDB is built internally to understand some kind of architectural principles that we can help customers build with as well. So one of those is high availability. And I can tell you that DynamoDB replicates data across 3 availability zones for high availability. But today we're going to go one step further in how we actually engineer for that high availability within DynamoDB. So a quick show of hands, how many of you have customers that come to you and say, we're absolutely fine with you taking, as an application owner, taking a downtime for maintenance of your database? None, right? So we believe that if you're building a highly available system, your acceptance to downtime for maintenance should be 0, right? In the last 7.5 years, I've not seen once where DynamoDB has sent like a notification to say, oh, we have a planned maintenance window that we're taking your database down for some time, right? You may not have seen any notification come in or an email come in to say just that. We believe that if database needs maintenance windows, your application loses availability. It's that simple. If you're having downtime for just maintenance of your database, you can't really build highly available systems. You need to engineer for highly available systems or applications, and for that, you need to have 0 downtime. So engineering for high availability is not sort of an afterthought. You can't really build an application and then think about, okay, now we want to introduce high availability on it, right? It has to be part of the design, part of the architecture, and part of the tenets in your building of that application and maintaining it. So we have a few rules that we've learned while building DynamoDB. And so we'll go through some of the rules and then have some examples of why it is important. Because clearly, if you're building applications for high availability, if we've learned something while building DynamoDB, you can benefit from those learnings as well. So Joe earlier mentioned that hundreds of customers do more than 500,000 requests per second on DynamoDB, right? If a developer comes to you and says that I've written this piece of code for the database and it fails once in every billion transactions. So every billion requests, it fails once. Would you accept that code? Absolutely not. Because at the scale that DynamoDB operates, that means it fails several times in the same day because you're doing hundreds of customers are doing 500,000 requests every second. So at scale, anything that can fail will fail. And so if you're engineering for high availability, you need to think about how can you avoid that, first of all. And if there is an outage, how can the impact be minimal? And so I'll share one example of that. How many of you know about DynamoDB global tables? Right? So it's a multi-region, multi-active, active-active database capability, which performs automatic replication across regions. And so here we have two architectural choices about how we went about building DynamoDB global tables. The top one has basically both have 4 regions, right? So your data is replicated across four regions across the globe. And we're basically using a replicator as a piece of software running on a host that does the replication between these tables. So if you write to any one replica, the replicator will take that data and replicate it across the regions. So in the first architecture, we have a single instance of the replicator, which could be a single box, a single host, running the replication for all the 4 regions. So if you make a write to US East 1, the same replicator is replicating it to the remaining 3. If you make a write to US East 2 first, the same one is replicating it to the remaining 3 replicas. As opposed to the next option of architecture, where we have individual replicator hosts for a source and destination pairing. What I mean by that is if you make a write to US East 1, there is an independent replicator host replicating to one of the other regions. And so in the top option, we have basically one instance, one replicator, right? In the bottom one, we'll actually have 4, or rather, we'll actually have 12, because what's not part of this diagram is you have a replicator on the source side, but also on the replicator on the destination side. So we have 4 replicas here, or 4 regions here. That means we have 12 replicator hosts managing the replication between all 4 of them. Now, clearly, the top one is going to be more cost efficient, right? But when we're talking about high availability, there's only one choice that gets you there. So if you're engineering for high availability, you have to think about, okay, what if one replicator goes down? You're still causing minimal damage because the other regions are still being replicated. And so we've gone with that approach instead of the first one. The next rule is what we've learned is about using simple components to build complex systems. So you don't go and build complex monoliths, right? Use really simple components and maybe loads of them to build your complex system. So DynamoDB could be a complex system internally, but it's built with very simple building blocks. Because simple building blocks have simple failure modes. Simple failure modes are easy to fix. And if you reuse the same simple components across your application, you fix one issue in a simple component and your whole system benefits from it. Your other applications using the same simple components also benefit from it, as opposed to building a complex monolith that would have its own peculiar failure modes, essentially. So in this case, a complex looking car could be built using small, simple Lego pieces. So this is like a block architecture diagram of how DynamoDB is built today. It's a collection of a lot of microservices, right? A lot of these services talk to each other in order to serve your single read and write request. Now, each of these services have a simple task to do, right? In Amazon, we call our teams as 2 pizza teams, which means each service should be owned by a team that can be fed on 2 pizzas. It's only small enough to feed on 2 pizzas. And so each team has a responsibility of their own service. There might be multiple services, as I mentioned, powering DynamoDB, but each different team is responsible for their service. They have an API contract, right? They tell you that if request router is building something, this is the API that other services need to call, and request router will do a certain piece of work in a certain time period, and that's it. And so they're responsible for managing their own services so that they can also do continuous deployments independently, right? They can fix their own simple component failure modes and be independent of the rest of the system. So you can't have a user that says, a developer that says, I've written some code and now I'm going to just deploy it to hundreds of thousands of nodes. Because at DynamoDB scale, you're actually affecting any change that you make goes through hundreds of thousands of nodes underneath. And DynamoDB is almost always deploying. So even if we say DynamoDB has no maintenance windows, the way we achieve that is slightly different. So at any given point, as long as you stay in the same availability zone for your deployments, there's always 2 other availability zones that are still supporting your data, supporting your request as your applications, right? So as long as we stay in those boundaries where we only deploy once in the same availability zone, you're engineering for high availability there. Now, as I mentioned, you can't have a developer that says, I've written some code, now hundreds of thousands of nodes, I'll just go ahead and deploy it. The way we do our change management or deployment process is, is similar to how engineering teams do it across the globe. What we do is we first do a change, we deploy it in a sandbox environment, would be the developer's local environment. Once it is committed, then it goes through what we call a one-box environment, which is a much smaller cluster of DynamoDB. Again, this is all pre-prod. Then it goes through a number of further pre-prod stages, and the cluster gets bigger and bigger and bigger. We go through alpha, gamma, zeta, before ever reaching production. And so zeta cluster is basically where we run a lot of non-critical workloads as well within DynamoDB. And you're still not in production, right? But any change that makes its way to zeta, we basically monitor for any changes in performance. Has the memory utilization of our system gone up slightly? Are the file descriptors increasing at a faster rate? Is the CPU going up? Because at the end of the day, it's servers that is powering your database. Any regression we see in performance, we immediately roll back. We roll back first and then think later. That's the basic slogan within AWS as well. So for engineering for high availability, you also need to make a system that is able to roll back fast enough. And you keep exercising that, right? Because let's say you don't have a plan for rollback and something breaks in your production, and you're only rolling back for the first time, that's going to be a bad day at work. So before we even get to the production stages, this is all that happens. So build a culture of any change in performance, roll back first, ask questions later. And to go through the other rules, I'd have Lee come up on stage.
Hi, everyone. Really quick introduction, because I think I'm tight on time. But my name is Lee Hannigan. Just like Aman, I'm a senior specialist solutions architect with DynamoDB. And you can probably tell by my accent, I'm from Donegal. Joe talked about how, I suppose, DynamoDB is a distributed system and some of its kind of key capabilities. Aman talked about how it achieves high availability. But I want to discuss with you why customers really choose to use DynamoDB. And the real reason is predictable performance. So Joe talked about this again, that applications at scale do the same things over. Are we done? Off. I didn't even get a try. The same thing over and over and over again. So think about your applications. Think about your applications that run at scale. Shopping carts, for example. Your shopping cart doesn't suddenly decide that it might want to do something like search. Shopping carts do shopping cart things. Search does search things. So it does the same thing over and over. Another thing that I want you to think about is that human beings can tolerate latency, but they'll find unpredictable performance intolerable. So you really want to make sure that it's predictable. So if we think about users visiting your website, let's imagine they're searching for an item in any sort of search API that you're serving, and it consistently takes 3 seconds. That user is going to be fine. That's a really nice user experience. But what happens if that user comes to your website and one time they search is 3 seconds, the next time it's 10, and then maybe it even spikes to 15? The user experience has severely degraded. They're not going to be happy with that system. So we need to involve predictability. So not only does it improve the customer experience, but it can also help you as engineers to effectively build your systems better, easier. We spend a lot of time at Amazon building predictability into our systems. Another way that I want to share with you is think of it as like 2-axis, where you have scale on one axis and performance in the other. You want to be in the top right quadrant. You want to be predictably performant at scale. And one way I can think about this is, imagine maybe Joe, who has flown here from Seattle, and that was a 10-hour flight. So he takes a 10-hour flight, and he's quite happy. It's Seattle to Dublin. It's quite a long flight. And he's happy with that. Anybody would be happy. You know what's in front of you. But you're sitting in the lobby or in the airport terminal, and you're waiting for your flight, and you hear an announcement saying that your flight has just been delayed by 2 hours. Now you're not happy. You were fine with 10 hours, but a 2-hour offset, it's not predictable any longer. You're not happy, and you want to think about that like your applications. So engineer for predictable performance. Engineers typically spend a lot of time doing this, especially with applications that run at scale. You'll analyze your trace metrics or build flame graphs into your application to understand exactly what every point in your code does. And we do that a lot at Amazon as well. And what we try to do is eliminate variance wherever possible. That is the key piece. That is why you're analyzing every point in your code, trying to eliminate variance. And I want to finish by showing how we done something like this in DynamoDB, where we eliminated variance where we could. So again, a high-level overview of what DynamoDB looks like. We have many, many nodes spread across multiple availability zones. So you have an application code running in AZ1. It resolved DynamoDB's endpoint for that region, and we terminate your request connection in AZ3. So we crossed a boundary in the AZ. We went from AZ1 to AZ3. Now we're doing a write request, so we need to write to the leader node of this replica group. So your data is always stored across 3 availability zones, but one of the nodes elects itself as the leader for that group. So again, we crossed the AZ. We're in AZ2 now, but we're not done there. When you make a write to DynamoDB, not only do we write to the leader, but we asynchronously replicate to the 2 followers. And we can't acknowledge your write unless one of the 2 replicas has returned an acknowledgement. We need to make sure that it's durably stored. So again, we've crossed the AZ boundary so many times that I've actually lost count. That's variance. So last year, what we did is we implemented 2 features internally. One, client-side local AZ routing, which we call CLAR, and the other is server-side local AZ routing, which we call SLAR. So what these 2 things do is, again, your application is in AZ1, and it resolves DynamoDB's endpoint. But this time, we attempted to terminate your connection in AZ1. Then, this stage, you're doing an eventually consistent request, where we also serve the data from the exact same AZ. So CLAR will make sure you connect to the same front end, and SLAR will make sure you connect to the back end, all within the same AZ. Total AZ traversals, 0. But it did say that we would do it wherever possible, and we eliminate variance where possible. So we're doing a strongly consistent read this time. And in DynamoDB, in its leader-follower architecture, we only know for sure that one of these nodes has the most recent data, and that's the leader for that replica group. Yes, we know that one of the 2 replicas, or the followers, had acknowledged the request, but at runtime, we don't know which one. So here, CLAR still does its work. It connects you to the same front end, which is in the same AZ. but Slar had no choice but to allow you to hop over to the other AZ to make sure that it served that consistent read that you asked for. So that's it from us. Aman, Joe, myself will be here. We're here all day. If you want to find us over here after, if you have DynamoDB questions, please come and talk to us. I am sure we will find some interesting topics to talk about in relation to your system. So thank you very much.